Okay, in this presentation we are going to look at simulation and random number generation and stuff like that. As part of a simulation study, an actuary is asked to design an algorithm for simulating claims for a particular type of insurance policy. The probability distribution of the annual number of claims on a policy is given as follows. So what could happen here on any particular policy? There's a 40% chance of no claims, 40% chance of one claim, 0.4, and for the probability of two claims is 0.2. Now, obviously, there could be more in that, but we'll just sort of go for a very simple setup here. So, just as a quick remark, if we were to sort of come up with a way of generating using the uniform distribution, what a particular probability, we sort of might use the cumulative totals there. So starting from the left hand side, 0 to 0.4, 0.8, and then 1.00. Okay, so what would happen, let's say, if we automatically generated a number, let's say 0.7932, that would be in this range of values here, 0.4 to 0.8. And in that case, what we would be simulating is an outcome where there was one claim. So it's very sort of simple setup using the uniform distribution to characterize a discrete distribution like this. Okay, so just to sort of start that off there. Now, the claim size distributions of the first and second claims are different. Okay, now this is in particularly focused on this part here. Okay, so if there's two claims, what happens? Okay, and really what we're looking at this one. Okay, so the size of the first claim follows an exponential distribution with mean 10, and the size of the second claim follows a Weibull distribution with parameters c equals 1 and k equal to 4. Okay, now what we're considering this setup as is as follows. So if there's one claim, of the first of any set of claims is going to be exponential, and if the second, if there is two, is Weibull. Okay, so this one would be exponential on its own. Okay, and this one would be the sum of an exponential, which is the first, and a Weibull, which is the second. So construct an algorithm to simulate the first claim on any given policy, which is exponential. Okay, construct an algorithm to simulate the second claim on a given policy, which is Weibull, and construct an algorithm to simulate the total annual claims on a given policy. So it's essentially coming up with the total sum. So I've partly described part C already. Okay, now, so essentially what we need here is to sort of, when we're doing these simulations and simulating exponential random variables using the uniform distribution and also Weibull, what we need is a cumulative distribution function here. Now, in this instance, this is the exponential one, okay? So this is the type of thing you should be probably used to at this stage. What I have here also is just as a quick remark that the mean is 1 over lambda, okay? So this part here is the key part here. I'll just write it out again. I'm going to use slightly different notation there just to make it a little bit easier to read. 1 minus the exponential of minus lambda x. So it's the exact same thing for x greater than 0, greater than or equal to 0. So it's the exact same way, it's just a little bit easier to read on the screen. And 1 minus lambda is the mean. That is just a quick remark there. Let's go and see what I mean by that. The mean here is 10. Okay, this is the exponential. So the mean is 10. That means lambda is equal to 1 over 10. Just to sort of make a remark of that later on. Okay. Now, the Weibull distribution. Now, there's quite a lot in this. So this is the PDF, the probability density function. Okay, using the standard notation, and this is the corresponding cumulative distribution. Okay, and I have it written there in terms of lambda and k as well. Okay, but the way we have things denoted is as follows. So we actually have terms, the our expression in terms of parameters c, which is the inverse of lambda, and then also k. Okay, so this is the key thing we're going to be looking at here. This is for the Weibull distribution. I'll just write that one out again. It's very similar in structure to the exponential. I'll use double brackets here. Okay, double brackets. So that's a C there. Okay. And yeah, so C and K. Now, just actually, that's what we need. Use that there. So it's a very similar sort of structure to the exponential distribution for the cumulative distribution function. So anyway, part A. This is when we're looking for. No, this is the exponential. This one, exponential. Okay. Now this is the sort of set game plan that we follow. We generate some number u. Okay, and we let that equal to the cumulative distribution function of x. Okay, and in this case what we have here is 1 minus the exponential of minus x over 10. Okay, now what we're going to do here is just solve that. So what we have here, 1 minus u is the exponential of minus x. Oh, I'm going out of shot there. I'll just move into shot a little bit. X over 10. Okay, get the logarithm of both sides. Now it's a little bit easier to read there, and just move the minus sign accordingly, and then we end up here is x is equal to minus 10 times the log of 1 minus u. So if you generate a number like u, let's say 0.7932, you just substitute it in there, 1 minus 0.7932, log of that multiplied by minus 10. Okay, and that will give you your exponential realization from the exponential distribution. Okay, so this is it here. So generate a sample u from the uniform distribution 0 to 1. Okay, and then perform this calculation here. We've just derived it there shortly. So that's the algorithm. Step 1, step 2. Okay, that's grand. So this is the Weibull in this instance, and really what we're doing here is something very similar to what we've just done before. So we have 1 minus the exponential of minus x to the power of 4. Sorry, let's just backtrack a second here. What were we told? Okay, so c is equal to 1, okay, and k is equal to 4, okay? So we don't really see c, if you get me. So 1 minus cx to the power of k. So we don't really, c is 1, so we get x to the power of 4, minus x to the power of 4. Okay? 1 minus x, the exponential of minus x to the power of 4. Do a bit of calculation there, or recalculate it, and we should end up as log of 1 minus u is equal to minus x to the power of 4. So we get x is the fourth root of minus log times 1 minus u. And then we just calculate it accordingly. You could actually also state that as, or state it in terms of the power of a quarter or something like that. Okay? So generate a sample u from the uniform distribution with parameters 0 and 1, max and min, 0 and 1, and then we get the fourth root. Just to be clear, that's the fourth root of minus log times 1 minus u. Okay, and so if you get some value u, just perform this calculation to get the corresponding Weibull realization, the realization for the Weibull distribution. Now, this last part here is calculate the total sum, come up with a way of simulating the total sum from any given year. Okay, so for policy, the total claim amount for any given policy. Okay, so we might, if we're generating on the basis of 1,000 policies, what we might do is run this algorithm 1,000 times. So as always, we start off with the generating a sample from the uniform distribution. Okay, generating a uniform random variable. So if zero is between, if u is between 0 and 0, 0 and 0.4, then the total claim amount is 0. Okay, and we stop. That's the no claims. Okay. So if if u, the random variable we can from the uniform distribution, if our simulated value is between 0.4 and 0.8, then we simulate a claim from the exponential distribution. Exponential with lambda is equal to 1 over 10, using the algorithm in part A, the first one, and set x equal to this value, and then we stop. Okay, so we only need to calculate one value there, the exponential, and then we stop. So otherwise, else, go to step 4, which means u is greater than 0.8. Okay, this is the two claim scenario. Okay, and simulate claims using the algorithms in A and B, and then set x equal to the total of those two simulated claims. Now, just as a remark, for this flow chart, we have one uniform random variable. Okay, just to decide if it's 0 claims, 1 claim, or 2 claims. Okay, but then we would also use the uniform distribution in part A and part B. So obviously you pick a different number there, use a different uniform random variable. Okay, so just be clear about that. Don't obviously just each time you need to use a uniform random variable, a realization, use a new one. Okay, don't use the same one for each. Okay, for example, in step 4, you should have, as well as this uniform random variable, which should be greater than 0.8, you need one for the y-bill distribution and another one for the exponential distribution. Okay, u1 and u2. Okay, just be clear about that. All right, we'll leave it there.